Welcome. We are in topic introduction to vector, and in last three video we covered this vector and linear combination. And apart from the theory, we have also covering with the questions and with the homework problem and with the homework solution. So if you haven't checked it out, I would recommend just look at this first chapter, first subtopic that I have already covered. Now in today's video, I will be starting with the next subtopic, that is the length and the dot product of this vector. So before starting, let me give you an idea what we want to achieve. So we will be we will not spend too much time on this topic. We will only simply look at what is length of a vector, what is a dot product, right? And with a few examples we will wrap this session. Okay, so in this video we are going to define dot product, length, and what the unit vector are. So last video what we tried to do is that, if you have already gone through, we were multiplying, or we were doing the scalar multiplication. We were multiplying a vector with a number, right? In this video, in the dot product, what we will be doing is multiplying the two vectors, right? So first of all, let me start with this dot product. So how we can do a dot product? So dot product is nothing but multiplication of two vectors. So let me start with the two-dimensional vector. So we can start with two-dimensional vectors, and let's look at that how we can do the dot product if we have two-dimensional vector. Let's suppose we have a vector v with the component v1 and v2, and let's suppose we have another vector that is w, and it has the component w1 and w2. Now how we can define this dot product is v dotted with w. So we can copy this v. So vector v has a component v1 and v2, and dot, and w has the component w1 and w2. Now how we do the dot product? We are going to multiply component wise. So we will be writing this as v1 and w1 and v2 w2, and we are not going to stop here, and we will be adding those two also, right? So this is how we will be defining the dot product, and dot product is nothing but the multiplication of two vector, right? So how we can do the dot product? We can multiply these two component wise and multiply these two component wise, and then after multiplication we can add those multiplication that will give you a number. So this will be a number, right? And this v is a vector, right? Vector, and this w is also a vector. So I just want to show you one thing here, and I am not going to extend or I am not going to stress too much on this point, is that you see that this vector v is from some two-dimensional space, and this is how we write there r is some real number, and this 2 is nothing but, it is saying that this vector v is from some two-dimensional space, and this w is also from some two-dimensional space. And what we are doing is that we are taking the dot product between this v and w, and what we are getting is a number, right? So you see there is some kind of transformation going on here, that if what you are doing, that you are multiplying this two-dimensional vector and it is getting mapped to some number, and this number will be nothing but a real number that you can represent with a real line, so with one dimensional. So you can think this dot product as some kind of transformation. So we will be not talking much about in this video about the transformation, but just to have this in your mind. Okay, now we can extend this idea even with the three-dimensional vector. So we can have the dot product with the three-dimensional vector and with the four-dimensional vector and with the n-dimensional vectors. So let me show you an example where we have, let's suppose we have n-dimensional vector, that is vector v. Obviously it will have the n number of components, so v1, v2 and vn. And let's suppose we have vector w, and this will also have the n number of component because it belongs to some n dimension space. So how we are going to define the dot product between this v and w is same way as we have defined in case of two-dimensional space. So it will be v1 to vn and dotted with w is w1 to wn, and again we can do the same thing. We will be multiplying component wise, and after multiplying component wise we are going to add all those. So what we will get is a number, right? So here we will multiply component wise plus v2 w2 plus dot plus vn wn, right? So okay, so far what we have seen is that how we can do the dot product, and dot product is nothing but of vector multiplication, or you can think it let's not think, let's stick to this, right? Okay, now let me take one example. So maybe in two-dimensional case we can take an example, simple example, just to give an idea that with the number, let's suppose, or let me do it in next page. Okay, so let's take example with a number. Let's suppose that we have some vector v from two-dimensional space, that is 4 2, and we have some vector w that is again from the two-dimensional space, that is -1 and 2. And if we have to find the dot product, that is v dotted with w, then how we are going to do that? So we have seen that we will be multiplying with the component wise, right? And after that we will be adding those. So -1 to 2, and what we will do, we will simply multiply the components, that is these two components and these two components, so 2 into 2, and then we will add these two. So what we will be getting is that 0, right? And every time we get this 0 in mathematics, that means there is something special going on. So in this case this v and w, this 0 says that if we are taking the dot product between through vector and if we are getting the result as 0, then what it says that the v and w are perpendicular. Okay, let me, I think we can use this symbol. So this perpendicular or orthogonal, that is the angle between, that is angle between v and this vector v and this vector w is 90 degree, right? So we can also look at this geometrically, right? So let me draw that one too. So let's suppose that we have our x-axis here, and let's suppose this is y-axis. So let me draw this first vector, that is vector v. So it has the component 4 and 2, and w has the component -1 and 2. So if we draw this vector v, then it will be somewhere here. So this is vector v, and if we have to draw this vector w, so it will be somewhere here, right? So this is vector, so this is vector w, and the angle between these two vectors will be 90 degree, right? So if we are taking the dot product between two vector, and if we have this 0, that tells that these two vector v and w is at a 90 degree angle. Okay, now let's look at the length of a vector. So how length of a vector, so how we can find a length of a vector is by taking the dot with itself. So if we have vector v, let's suppose we have some vector v that is from our two-dimensional space, and if we have to find the length of v, so what we can do is that, so we can take the dot product with itself, right? And let's suppose that this v has the component v1 and v2, right? So if we take the dot product with itself, then let's see what we will be getting is this, right? So we will be what we will do, we will multiply component wise and then we will add up. So if we do that, we will have v1 square plus v2 square, right? So if let's suppose that this is your vector v, right? And if we have so what we are doing is that we are taking the dot product with itself, right? So and okay, so we can think like this. So let's suppose this is two-dimensional space and we have this vector v here, right? And this is the component v1 here, and this is a component v2 here, right? So if you see that if we do the square of this v1 square and do the square of this, that is v2 square, right? So what we see that this is nothing but v1 square and this is v2 square, right? And if you see from the Pythagoras that the length of this one will be v1 square and plus v2 square, right? Root over of this v1 square and v2 square. So if we are taking the dot with itself, what we are getting is the length square. So we can say that the length squared, that is equals to v dot v is equal to v1 square plus v2 square, right? Then what will be the length? So we can say that length of v, or we also write it as the norm of v. So this is nothing, you can read it as norm of vector v, right? So that is equal to root over v1 square plus v2 square, or you can write it as v dotted with v, right? So this is how we can find the length of a vector. So we looked at the two-dimensional space. The same idea can be extended to the n-dimensional space. So let's suppose that so this is the length, right? So let me okay, and this is a norm of v, you can read it as norm of v, right? So and so let's suppose we have this vector v that is equals to that belongs to some n-dimensional space, and let's suppose we can write it as that belongs to some n-dimensional space. And if we have to find the length of this v in this case, so how we can do that? So it is simple again. We can do analogous to what we have done in the two-dimensional space. So we can take the dotted product, and this will give you the length squared. So that will be v1 dot vn, and dotted with this v1 it dotted with this itself, right? So we will be getting this v1 square plus v2 square and dot vn square, right? And this is nothing, this is length square, right? But we have to find the length of this v. So length of v is equals to root over of v1 square plus v2 square plus dot vn square, right? So this we saw this for two-dimensional case, and we extend our idea to find the length of a vector in n-dimensional space, right? Okay, so since we have looked at the length of the vector, now we know that how to find the length of a vector. Let me just give you the formula for the cosine formula, and I am not going to look into more detail on this formula, but let me just give you the formulas. So if you want to find the dot product with vector v with this vector w, then this is nothing but this is equal to the length of this vector v, or you can say the norm of this vector v, or into norm of this vector w, or you can say the length of this vector w into cos theta. And here this theta is the angle between this vector v and w. So you can think as this, if this is a vector v and this is a vector w, then this theta is the angle between this vector v and w. Okay, now I will be not going into much detail about this cosine formula. So and this, if you are getting this dot product 0, then what it tells that the angle between this v and W is 90 degree, right? So yeah, so this is your cosine formula. Now let's look at the unit vectors. Okay, now let me define this unit vector. So a unit vector is a vector. If you find the length of a unit vector, what you will get is a 1, right? So let me write it down. A unit vector u, let's call this unit vector u, is a vector whose length equal to 1, right? Or equivalently, what you can say, if you are taking the dot product of this matrix, sorry, if this vector v, sorry, not this vector, how, what we are calling this unit vector as u. So if you take the dot product of u with itself, then that will give you the length square, and if it is a unit vector, what you will get is 1, right? So length square, or you can say the length is going to be 1, right? So let me get an example for this. So let's suppose we have this vector u that belongs to some 4-dimensional space. So if this u is a unit vector, then it will have the component 1 by 2, 1 by 2, 1 by 2, and 1 by 2. Now if it is a unit vector, then if we find the length of this vector u, then what length is squared, or you can say length of this vector u, then what you will get is 1, right? So let's do that. So if we find this, then 1 by 2, 1 by 2, and 1 by 2, and 1 by 2 dotted with itself, so what you will get is this, right? 1 by 2 is square plus 1 by 2 square plus 1 by 2 square plus 1 by 2 square, and you carry out the calculation, you will get 1, right? Now sometime what will happen, you will ask to find the unit vector in the direction of some vector. Let's suppose you have given this vector v, and you will be asked to find a unit vector in the direction of v. Then in this case, how you will find that? So let me first write down the problem. So what we want to do is that, let's suppose given a vector v, we can find a unit vector. Let's call this u in the direction of in the same direction, you can say in the same direction as v, right? So we want to have this unit vector u, right, in the same direction as v. Let's suppose you have this vector v, right, and this vector v is given. What we want to find, this vector u, that is a unit vector, and it is in the same direction as v. Same direction, I mean to say it will be on the same line. So this is not the only vector u that will we will have also this negative u. So it will be on the same line as v. So this will be also there as minus u. So how we can find this u that is in the direction of v. So for that you will have this vector u that will be in the direction of v, right? And since it is a unit vector, what we are going to do, we are going to uh, divide it with the length of this v, right? So this is a unit vector in the direction of this vector v, right? Or we could have this negative one also, right? So for that you will have this unit vector u with the negative sign, right, in same direction as v. And what we, since u is a unit vector, so what you will do is the divide this by the length of this vector v, right? So this is how we can find a vector, a unit vector that is in the direction of some other vector. Okay. Now let me just give you two inequalities, right? So this is not important but good to have. The first one is we call that Schwarz inequality. So Schwarz inequality. So what does it says that if you take the dot product of this vector v and w, and if you take the absolute value of this dot product v and w, that will be equal to less than equals to the length of this vector v and the length of this vector w, or you can say the norm of this vector v and the norm of this vector w, right? So this is what we call the Schwarz inequality. And what does it mean that if we, so how we can look at this, let's suppose we have the cosine formula for the dot product, that is v dot w is equals to the length of this norm of this v and norm of this w and cos theta, right? Now if we take the absolute value, right, so we can take this absolute value both side, so that will be equal to the length of this v and this length of this w, right, and the absolute value of this cos theta, right? And we know that this value is less than equals to 1, right? So we can say that the absolute value of this dot product will be less than and equals to the length of this v and the length of this w, right? So this is the Schwarz inequality. Now we have one more inequality, that is the triangle inequality. And what does it say? That the if you add two vector and if you take the length of that vector, that will be less than equals to the individual length of the vector v and the vector w. So again, how you can look at this, let's suppose you have this vector v and this vector, maybe this vector w. So this vector v and this vector w. So what will be the v plus w? So that will be this vector, right? And this is v plus w. Again this will be v, right? So what it is saying that the bigger size, the biggest size in a triangle, that is this one, the length of the biggest size in the triangle, that will be less than equals to the sum of the length of individual this length of this triangle, right? So it is not that important, but let's have this one also. Okay, now we will look at simple problem, and we will wrap up this topic. So you see that we haven't gone through that much of in more detail. So before starting the lecture, I told you that we will be looking just the terms, and we will be looking that how it is defined and all these things, right? And so we will look some problem based on this length and dot product. That's an easy one just for the sake of the practice. And then we will jump to this chapter 3, that is matrices. So based on uh, syllabus, uh, so where I will think that needs the more explanation and needs more time, I will be spending more time, because you have seen that in lecture 1 we have spent almost 3 lectures on it, right, to make you understand that what is actually the linear combination is. There is lot to talk about this on this dot product, right? I haven't given you the uh, geometrical interpretation of this dot product. We will look at this more on this projection, right? And yeah, so we have gone through this length and dot product. Next lecture we will go through some problem, and you will have some assignment based on that particular topic. And in the next lecture we will close this topic, and then we will move to third topic, that is matrices. Okay, that is all about this lecture. Thank you.